Hello, my name is Mantasha Ahmed, and I will tell you about the methods of nuclear physics, like in modern nuclear physics, how uh, we make it useful for our biological system, and how the uses and its property are interlinked with our human body. So, in modern nuclear physics, which make use of powerful beams of elementary particles like electron, neutrons, uh, X-ray beams, and there are gamma rays. Several rays are present in beams of elementary particles. They also offer such methods such as X-ray diffraction using synchrotron radiation. Like I will tell you what is synchrotron radiation. Synchrotron radiation is the radial radiation, um which is dissipated, or we can say which is ejected in a radial manner through ejectory in a ejectory path from the circumference of its trajectory circular motion. So here you can see on photo how it's look like. Now, how this synchrotron radiation and X-ray diffraction using these synchrotron radiations and neutron diffraction is similar to this, how they are useful for dissolved biopolymers to know their molecular structure and super molecular structure, like on very infinite, or we can say to the very basic level of their organization. Magnetic bremsstrahlung or synchrotron radiation arises during the motion of charged particles, say electron, in cyclic accelerator. In synchrotron radiation, the energy spent for acceleration of particle is lost. Synchrotron radiation is in the X-ray region of the spectrum, has an intensity two orders of magnitude higher than the modern X-ray tubes. Like there are different range, as you can see in this photo here. So we can see here, like there are different stages, UV rays, X rays, gamma rays. They have their own places in the absorption spectrum, how they are arranged. But synchrotron radiation, as I am saying, is two more points higher than X rays. So what we do in this, we do X-ray tube of power 2 kilowatt is taken, and it is the device is ejected with heavy metal electrons. So the radiation beam which is ejected by them in a radial trajectory manner, that is synchrotron beam. Now this synchrotron beam, when we see this, in this we see this X-ray absorption edge shows the fine structure of absorption band, as you can see here in this photo. The graph which represent the peak of this is the where absorption is the maximum for synchrotron electron. Now, how we calculate the wavelength or the frequency of this electron, or the frequency of this beam which is ejected from this heavy metal of molybdenum atoms. This is usually done with molybdenum atoms. From de Broglie wavelength, we know this formula, as you can see here. Lambda is equals to h by mv. So here h is the Planck's constant. We know that m is the mass of the particle. The particle here is what? Synchrotron atom, or we can say X-ray atoms or molybdenum atom, which we are taking in consideration. V is the velocity at which it is traveling, and magnitude and distance is to be calculated between the object and the particle which gets collided with the atom. So this magnitude or of the distance which is to be calculated, this is calculated by de Broglie wavelength, and the wavelength which is lambda, this is to be find out. The beam of neutrons from an atomic reactor is subjected to monochromatization by reflection from a crystalline plate, say from calcium fluoride. Diffracting neutrons are recorded by counters. The neutrons are scattered not by electronic shell of the atom, but by its nucleon. And the atomic scattering factor is determined by the proton neutron structure of nucleus rather than by atomic number. So the neutron number of neutrons present We know that number of proton is equals to number of neutrons, and the electron is equal to the number of protons, but it is never equal to the number of neutron. Electrons are never equal to the number of neutrons. So here the structure, the factor, this is scattering factor at which the ejectory path, it is dependent on proton and neutron both. The structure of that, in nucleus neutrons are present, rather by atomic number of a element, as we know from for sodium it is 11, and by it will not be determined. So the number of neutrons present in it will determine it. The atomic factor for hydrogen, that is for the proton, is far from being minimal. Therefore, in contrast to X-ray diffraction, diffraction allow hydrogen atom to reliably located. For instance, like neutron diffusion can be employed for establishing the detailed structure. It has been shown that hydrogen atom, which forms covalent and hydrogen bonds with O, like electronegative atom, we know that fluoride, oxygen, and nitrogen. These are the three atoms with which the hydrogen forms the hydrogen bond. So this is the electronegative hydrogen bond. Is, in other words, we can say it is a electronegative force between the molecules. So the two positions of the electron which is to be acquired by the hydrogen, one is taken from the oxygen and the other electron is of hydrogen itself. You can see in this picture made two positions which it is occupying. In other words, the proton may reside near its own oxygen atom and near a foreign oxygen atom. The hydrogen bond in water is characterized by jump of protons between two equivalent minima. Neutron diffraction has been successfully employed in investigation of biopolymers. Like there are different biopolymers which are very necessary, and their structure to be known is very necessary. Like DNA, we know DNA is a biopolymer, and there is a cellulose. Cellulose is also a biopolymer. Cellulite, keratin, these all are biopolymer for which we are interested to know their molecular structure. As regards the diffuse scattering of neutrons by the solution of biopolymers, like if here is a beaker and a light of beam is passed through it, so the scattering that is taking place from this side of the beaker, so it will result in a scattering of x-rays, and these x-rays have a very important significant role in medical field, as a biological object can vary the overall amplitude of the neutron scattering. This reveals the selective scattering of different functional group, and possible it has made possible for us to investigate the nature of the complex formation of protein and DNA in chromatin. From this we can also decode its structure. A specific method of structural studies of biopolymers is gamma resonance spectroscopy based on Morse-Bohr effect. You can see here, this depicts the summary of Morse-Bohr effects and how this has to be explained, or this is determined. This effect consists of resonance absorption by atomic nucleus of monochromatic gamma radiation emitted by a radioactive atom. Like there are several radioactive atoms. Um, we will take any one of these radioactive atoms, like cobalt, the 57 cobalt, it is a radioactive atom. We will take atom from this, and we will bombard it gamma radiation on it, irradiated on this radioactive atom. So from this we can take this extra x-rays which comes out, and these can be used for like seeing the tissues, the bones which are present in our body. Fe containing, like there is a electron, what we say, a radioactive atom, 57 Fe also is all present. It makes us possible for Fe containing proteins like hemoglobin, myoglobin, and cytochromes. These structures can also be studied with help of this gamma radiation emitted by radioactive atom. The sample is exposed, this the sample which we will take, like if we have to study the structure of hemoglobin, then we will take a sample of it and we will radiate it with gamma radiations. If the source is made to move at a low velocity relative to the absorber, that is the sample under study, along the axis that connect the source and the sample, the frequency of the gamma quantum will be changed a little due to Doppler's effect. Now this is the Doppler effect. So it states how the frequency and the low velocity of the electron which is bombarded, it changes the y-axis or the direction, and by which we can know the frequency. We can determine the frequency of that. Now, at the certain value of natural frequency, samples will absorb gamma quanta resonantly, passing from the ground state to the an excited state. Like electrons present in its orbital are in ground state. But if certain amount of radiation or energy or a photon is bombarded on it, so like this you can see here. So when it is bombarded on it, the electron gets excited, and from ground level it is excited to one energy level of one orbital higher. So we say it to be excited state. The resonance frequency of the Fe nucleus in heme. The iron present in the heme core and other Fe containing groups is highly sensitive to the action of neighboring atoms and group. This enables one to obtain information on the electronic structure of Fe containing atomic groups in their various states in protein. The effect can be enhanced by enriching a biopolymer with the Fe isotope. For this purpose, the content of this isotope is increased in food of the animal under test. So this is how gamma electroscopy and X-ray diffraction is useful in modern biology and in human anatomy and in medical field.